finished off the axial skeleton by talking about the ribs and the sternum, and now we're moving on to the appendicular skeleton. This is part of the skeleton that is devoted to the limbs, the ability to move about, grab things. And girdle. So when we talk about the appendicular skeleton, think about our upper limb. We start with the clavicle and the scapula. You might think of these as like your collarbone and shoulder blade are often common terms to describe these. They are not the anatomical correct terms for them. And then you have, I should categorize these. These are basically part of the pectoral girdle. And then you have the upper limb. And that's going to include the humerus, which then articulates with the radius and the ulna together to form. So think about these. Basically, this is often described as your arm. You can think your arm as your entire upper limb. That's really just from your elbow to your shoulder. And this is often referred to as the forearm. That's a common terminology, and we'll stick with that because the book doesn't go into correct anatomical terms for these. When we think about connections here, it's the scapula that connects to the humerus. The clavicle connects to the scapula. And then what I don't have on here is the clavicle itself is connected to the sternum. So we think about how all our bones connect and what connects to what. And then the radius and the ulna are both connected to the humerus in the forearm. That's these two bones in here. And these in turn are going to articulate with a whole bunch of bones called carpal bones. And you might think of these as your wrist, even though in some respects they form part of the bottom of your palm. These in turn These in turn are going to articulate with a group of bones called the metacarpal. And then finally, these will articulate with your finger bones or what is called the phalanges. So think about your metacarpals as being your palm and your phalanges as being your fingers. Over here on the lower limb, we start off with girdle 2. We have what's called the pelvic girdle. And this is actually formed by two bones called, well, I really like the word, the more anatomically correct, os coxum. This basically means bone, coxal bone. By the way, OS is acceptable scrapple. So you have two of these, and they come together and they make their connections back to the axial skeleton through the sacrum. The sacrum is really the linchpin that holds this whole girdle together, forms a nice circle, and gives us a stable base for our upper body to rest upon, or our lower body. The V's in turn will start to go into the lower limb here. We start to see a similar pattern. We go into one bone called the femur. And this in turn articulates with, you think, two bones, but actually it articulates directly with the tibia. It does not articulate with the other bones in your leg. There's actually two bones down here, just like there are two bones in your forearm. But this lighter bone on the side here does not actually interact with the femur at all. It acts as a support strut at the top of the tibia there. So I'll put fibula here because it's in the same region, but it's not articulating with the femur. So you might think of this as your thigh. This you might think of as your leg. Depending what else to call that. From your knee to your heel, it is anatomically your leg. And then both the tibia and the fibula together are going to articulate with your tarsal bones. So these are the equivalent of the carpal bones, except for the tarsal bones are interesting because only one of them really articulates with these two bones. The rest form the back third of your foot. So this is like both ankle and foot. So these part of your foot. These in turn are going to articulate with a group of bones called the metatarsals, which are also just your foot, the anterior third, and then those, and again, we come back to the phalanges, and those are more of your toes. That's a very simplified way of looking at the skeletal system. I've missed something. But there is a unique bone in our lower limb that doesn't follow the pattern at all of the upper limb, and that is the patella. And so, in terms of what is the patella, probably right about here. The patella is actually articulated with both the femur and the tibia, and you think of this as your kneecap. A lot of people call it that. That's that bone sitting right there. So again, it's a relatively simple way of looking at it because, if we're doing full anatomy, we get into all the carpal bones and the tarsal bones. And so let's see what we have in store for ourselves. What do we have to turn These are things I'd like you to be able to remember about the navigator skeletal system. For example, the clavicle connects to the manubrium of the sternum. So we made that connection over here, where I mentioned the sternum is connected to the clavicle. The scapula actually has some unique features associated with it I'd like you to know about it. One is the glenoid cavity. The glenoid cavity is a part of the scapula. This is this bone up here. And there's pointing to the glenoid cavity, that's where the humerus meets it. So, in terms of looking at the scapula, there's this cavity right here. And then the rest of the scapula is sort of triangular shape. And the head of the humerus fits in like so. So this is the glenoid cavity here. It's that space, the socket in which the humerus fits in there, which is why it's important. And then attaching to the humerus a whole bunch of ligaments and tendons that ultimately form a giant cup around the humerus and scapula called the rotator cuff, because the actual cavity, the glenoid cavity, is relatively shallow. It's pretty easy to disarticulate or dislocate your shoulder as compared to your hip because of that. But the benefit of having such a shallow cavity is that we can do this. We can move our arm around all over the place. There's freedom of movement, and it allows us to interact with our environment in a very excellent way. rotator cuff is a bunch of ligaments and tendons. Muscles. That's where tendons come into play. We'll talk about muscles. And they have to sort of strap those two bones together. In terms of the humerus bone, some features we should be aware of for that, including the deltoid tuberosity, so swelling on the side of the bone. That's where the deltoid muscle, the big shoulder muscle here, attaches to the humerus, allows you to get your hand like this. So it's a really important connection point for the humerus. And then, in terms of the capitulum, that's a part of the humerus that the radius is able to articulate. So the capitulum is where the radius articulates. Did I get this? So we're talking about the humerus. Deltoid tuberosity. And then we'll put a shorter humerus. So the radius is here, the head of the radius is here. This is the capitulum. And this is the radius here. I do a lot of drawings to help me remember things. Now here, this little area is called the trochlea. And that's important because the ulna is here. The ulna has this piece that goes all the way back called the olecranon, or elbow is. So it's actually behind there too, and it fits in front of the trochlea. So the trochlea is important to the articulation spot for the ulna. Now the radius here, it says the head. This is the head of the radius right there. It's the part that's articulating with the capitulum. But for the ulna, you're going to go all the way down here to the other end of the donor thing before you cover his head, which is down here. Oh, I've got the stylish process, but it's our thing to go to the other thing. So a total of 8 carpal bones in here. They all have a name. Then you get the 5 metacarpals. These are again your palm bones, so they're forming the palm of your hand. They're not for your digits. One for each of them, though. One metacarpal for each digit. And then you have 14 phalanges. You're thinking, wait a minute, I got 5 digits. How does 5 go into 14? It only works because your thumb only has 2 phalanges. Everything else has 3. Think about how you can bend your fingers. You've got 3 different bones there. This one only has 2. So that gives us a total of 4 times 3 is 12 plus 2 is 14. Between both hands, you go, hey, start doing some math. So math and human biology. Questions? So, more towards that outline here on the board. So we start off with the hip bones. The hip bones are pretty actually have a lot of structures on them. First of all, the hip bones are so large that they actually have 3 different regions. It's really hard to draw the hip bones. This is sort of generic, not very good. There. So this is the ilium, the pubis, and the back here is the ischium. This is the part you all are sitting on right now. People talk about their hips, they're usually talking about the ilium. Here. And the pubis is the pubic region is up front, and the ischium is the part you're all sitting down and cheating around. I have no armpits, I have no armpit. As I mentioned, the pelvis, the whole pelvic girdle, is really, really tied deeply into that sacrum and a little bit the coccyx. It's certainly hanging off of that, and it's what creates this stable platform on which we rest the body. If you consider the upper limb here, it's only connecting to the nerve through the collarbone. This is one little thin bone here. But the pelvis has got these 2 massive bones that are linked in front and linked in back by the sacrum, which holds it together. And then right about here, there's going to be a big, deep socket called the acetabulum. And it's not too confusing with this big hole that's down here. It's called the obturator foramen. This is not all the way through. It's just a socket, whereas this is an actual hole here. I don't think we're doing the obturator, so we don't have to worry about that. So the deep socket, the acetabulum is a deep socket. You can see where the head of the femur is inserted in there very solidly. And the 2 coxal bones come together and they meet at something called the pubic symphysis. It's a place where they're glued together by fibrocartilage, so it's a cartilaginous joint that's holding them together. If you were to compare female and male pelvises, you would see distinct differences between them. You can differentiate between the female and male pelvis just by looking at the bones. And that's because of things like the pubic angle, the fact that it's much wider, the hips, they flare out more. Ultimately, it creates a more rounder pelvic inlet, which allows the baby to spend faster. When we look at the femur itself, the femur has got a pretty rounded head, and then it has a very narrow neck. It's got a couple of large protuberances that are called the trochanters. And it goes way down here and forms 2 large conti. So head, neck. We're not naming the trochanters, just saying that there are these 2 large places for muscles to attach. They're called processes, so we'll call it that. And ultimately down here, it articulates with the tibia. On the knee joint. In front of all of this sits the patella. And the patella is an important bone because it transfers force from the big quadriceps muscle here down to the tibia. bones, and he's missing one patella and one of the legs. I think it's congenital. I think they just never had it. They had to have it removed very young. And they have real difficulty going downhill, not uphill, but downhill. And they rely upon that patella to help raise them. So they have to slow down and find out. The patella itself, which is, again, actually, I'm trying to follow this. Make it more realistic by hiding all the bone that it's hiding. Actually has two important structures that attach to it from the top. And then this leads to a very large muscle called the quadriceps muscle. It has four large heads. And so this is called the quadriceps tendon. And it's called a tendon because it's attaching a muscle to a bone, and then down here, continuing down, we have really the same connective tissue, and now it's connecting the patella to the tibia, so we call it the patellar ligament. And where it attaches to the tibia right here, there's a raised part. It's called tibial tuberosity. Those are crazy. They call this tibial tuberosity. It's on the tibia, but it's the patellar ligament that attaches to it. They call this on the arm the deltoid tuberosity, even though by this logic it should be the humerus tuberosity. So it's named based on what muscle attaches to it or what bone is found on. There is no absolute rule. And then again, what we have here, we find the fibula would be coming in over here, acting on the lateral side of the leg. That broken fibula. You don't want that. It acts as a support strut, maybe sort of as a protective brace on that side. You don't want to break the tibia, you don't want to break the fibula either. You can still get around with a broken fibula, but not with a broken tibia. And then my drawing is coming to an end, so I can't get it down. That leads to the foot, which is going to include the tarsals, which are the equivalent of the carpal bones. So we're thinking of ankle bones, but in reality, only one of these bones forms the ankle joint, and that is the talus. So the talus is important because it articulates both with the tibia and the fibula that form your ankle. It makes your ankle joint more akin to a hinge joint, but it's not exactly. It does have some ability to move in all three dimensions. The other big tarsal bones, so we didn't learn any of the names of tarsal bones, but there's two tarsal bones that are considered important enough to learn the names. One obviously is the talus because it forms your ankle joint. And the other one because it forms your heel, and it's the largest tarsal bone. It's a pretty hefty bone called calcaneus. So when you strike the ground with heel, that bone there, that is one bone called the calcaneus bone. You only have 7 tarsal bones. You have 8 carpal bones, but you only have 7 tarsal bones. And it's probably because the calcaneus is actually 2 bones that are fused together to serve the purpose of allowing us to run. Because our primate ancestors did not. And it's also a point for muscle attachment. We'll talk about later. It allows us to stand on our toes. Beyond that, we have the metatarsals that I mentioned forming the first, basically the arch of the foot. And then you have 14 phalanges again. You have 2 phalanges in your big toe, 3 in each of your other toes, including your little pinky toe. So it comes through. It's a big comparison to what we saw earlier in terms of evolutionary background of primate forebears who were in trees. questions? All right, the fastest adductor skeleton ever presented by every semester for biology. So articulations are basically joints where bones come together and meet. So the bones then move relative to each other. There are lots of ways you can classify articulations, and a lot of those will actually classify them in both functional and structural ways. But in this case, it's kind of been all been compressed into one way of doing it. We're going to talk about it structurally, but at the same time, we'll talk about it they can do functionally. So the first two are very clearly based on structure. The first one being fibrous tells us that the bones are connected by fibers. And when you have that type of connection, at least with the limited scope of the articulation we're talking about, those bones do not move relative to each other. So the sutures of the skull are the example. I'll just show you where those are. Up here, and a picture of the skull here. And wherever you see these two bones meeting, you see those squiggly lines. This is a thing called the swallow suture. There's one back here. There's one up there. They're all over the place. And these bones do not move relative to each other. The reason why the baby's skull can have some movement is because it retains some of that fibrous tissue between the bones and expands it. So there's these soft spots that allow for some movement. But by the time we're adult, it's all gone away, and it's become a very solid connection between the bones. So, fibrous connection, sutures of the skull, not movable. That's pretty easy to remember. It's pretty easy to categorize that zero movement. You've got fibrous connection. Cartilaginous movement, the example they give us is the bodies of the vertebrae and the costal cartilages. So I can show you those. Move here, they start up here. We can see the costal cartilages, that white area here between the sternum and the actual bone of the rib. All that cartilage allows for some movement so that the ribcage can lift up and go down so you can breathe. Raise up, come back down. So it allows for slight movement. You see the bone is connected to another bone by a solid band of cartilage. And then we look right above it at the ribs here. And when it comes to cartilaginous connections, they're talking about right in here where the big bodies of the vertebrae come together and they connect. And that cartilage allows for some slight movement between the bones, but not a lot. That's interesting because there are other types of articulations in here that are synovial, the superior articular facet of the vertebrae, for example, allows for a synovial connection. It allows for more freedom of movement in that particular joint. So that brings us to our conundrum. Slight movement versus freely movable. Where do you draw the line? When do you become freely movable? And when I talk about synovial joints, I like to say, well, synovial joints are where the two bones move freely against each other because they're not directly connected to each other. They're connected on the outside by things like tendons and ligaments that hold the bones together, but there's not really a direct connection that's holding one bone against the other. Again, it's sort of vague. Because even there's exceptions. In fact, particularly the knee joint right here, there are actually ligaments within the knee joint that hold the tibia to the fibula to the femur directly. And up here in the head the femur, there's actually a ligament that comes out of this well-known synovial joint and attaches it to the hip bone so that it does not dislocate very easily. So there are some examples of synovial joints where there is a direct connection from bone to bone. But the amount of movement is still greater than the cartilaginous joint. But at what point do you cross over and say for sure that that's freely movable? We don't. We just sort of describe it that way. I think the one way to really focus on the difference between synovial joint and cartilaginous joint is that one, cartilage is not ever doing that connection between the two bones. We will find some dense fibrous connective tissue, but we will not find cartilage. And the other thing is that the presence of something that is not found in either one of the other types of articulations, and that's this, the joint capsule. The two bones that are connected are ultimately encapsulated. There's something that surrounds them called the synovial membrane. And that synovial membrane then produces a fluid called synovial fluid, which acts as a lubricant. Because the bones are have movement against each other, where the two bones are actually rubbing up against each other, there are a number of features that help reduce the friction. One of them is actual additional cartilage. So if you actually look at the surface of these bones, on top of the bone, there's going to be a layer of hyaline cartilage. On all examples, it helps to round off the bone, helps make it really smooth. That's what this particular cartilage is. And this in itself is equal to hyaline cartilage. That's the type of cartilage it is. And this is often known as smooth cartilage because it is so smooth. It is, of course, the most common because every bone has it. And it's the weakest of the three cartilages we're going to talk about. It doesn't have particularly a lot of strength. That's not its specialty. Its specialty is reducing friction. It still has a strength. It's just the weakest of the three. Doesn't mean that the three cartilages aren't all strong. You just have to, in comparison, it's not as strong as the other two that we'll talk about. The articular cartilage fits all those categories. And of course, the other thing that reduces friction is this fluid, which is derived from adipose tissue. So a lot has a lot of fat in it. That sort of smooth, lubricant feeling that oils out. Synovial joints are going to have ligaments. They're either going to have ligaments on the outside, like this patellar ligaments. They might also have ligaments over here, like what's something called the fibular collateral ligament. And over here you've got the tibial collateral ligaments. And they help to form part of the capsule. But in addition, the knee joint has internal ligaments called the cruciate ligaments. They help stabilize that knee joint. We rely so much upon that to be able to stand up. So there'll be ligaments there, and there's also going to be bursae. Let's do a side picture. don't want to have any friction between the pellet here, which would of course make it more cartilage here, and then you have the pellet ligament here. And you don't want to have any friction between that ligament and the tibia down here. Well, you're going to put a little sac in there. You're going to put some synovial fluid in there, and what you get is a person. And that reduces the friction between that ligament and the bone. There's a little pillow there. This can be, however, inflamed if you get a condition of bursitis. In fact, there's actually even one of these right about here, between the skin and the bone, to help reduce the friction between the bone and the skin. When that gets inflamed, it can cause swelling in the knee and it'll pull out water on the knee. And then the only place where meniscus is found is the knee, as far as I know. So within here there's another type of cartilage called meniscus. This is what they need on lateral. This is made of fibrocartilage, the strongest of the cartilages. It helps to stabilize that knee joint. People do not want to lose the meniscus MID, that results in a lot of pain. It's just not built to deal with the forces of that impact of the knee joint as the meniscus goes away. A couple of examples of synovial articulations include the ball and socket joints, both of the hip and the shoulder housing, allows for three-dimensional movement. A little less for the leg, but you can have some of that. Maybe more, depending on how limber you are. Might not particularly limber. Although I can still hold blood. Too busy training for one marathon. So I want to just make some notes here. Ball and socket. Three-dimensional movement. So these are the most movable of your joint articulations, your synovial joints, of any joint. And then hinge joints are also very movable, but they're only two-dimensional. Like a door, you have this your elbow, there's a hinge joint. In and out. Shoulder through all of this. The ball and socket is a lot more freedom of movement. Your knees, same deal. Kick your heels up. And that's not about it. You can rotate your leg. You get a lot more movement out of the ball and socket. Questions? All right, so all those articulations, all those synovial joints do allow for some movement. And we're going to be talking about muscles next, even though they will not be on the lecture exam that you're going to have next week. This week you're having a lab exam, next week you're having a lecture exam. So when we talk about those movements or those muscles and their actions, we have to have some idea about what those terms mean. Flexion and extension. So flexion basically is to decrease the angle between two body parts. Flexion decreases angle between all parts. So we see some flexion of the arm, you can flex your head, between your chin and your chest there, you can flex your leg, take your heel up, or you can flex your hip and your knee up. Of course, every single one of your fingers can flex. So we have flexion, you have extension, you have flexion, you have extension, you have hyperextension. Abduction moves a body part away from the body. Abduction moves body part towards midline. So, abduction moves your arm away from midline. Adduction brings your arm towards the midline. You do that for your leg. Abduct, adduct. You can do that with your fingers. This is abduction. This is adduction. See them doing their legs and arms up there. So those terms go together because they're basically opposite. Rotation and circumduction don't fit that category. Rotation moves a body part around its own axis, so we rotate our head and stay in a little bit. We can also rotate our arms, our legs. Circumduction, we move the body part in order to define a circle. So when I'm moving around, I'm rotating on the axis and define a circle. You can do your head too. Don't do it too much. Do with your leg. Body part moves so that a cone shape is developed. Draw a circle on your face. Supination and pronation are particular moves that are specific for the palm of your hand. If you turn your palm of your hand to the posterior side, to the back side, that is pronation. Turn to the posterior, pronation, P for P, and supination is turning the body forward, supplication, supination, pronation. Forward, pronation, long, do that. Just to show you, there is a difference here between pronation and supination, versus rotation. Rotating the entire arm here. And that does cause what it looks like pronation and supination, but I don't need to move my shoulder to do pronation and supination. I have three muscles that are most helpful for that. Inversion has to do with your foot. So if you turn your solar foot inward, you're not going to get it very far, typically. That's inversion. If you turn it outwards, it's eversion. So inversion version. So we'll put up. Questions? All right, let's take a 10-minute break. Osteoblasts they build them. So you need bone, you need osteoblasts. Osteocytes are what osteoblasts become. Once they're done building, they are embedded in bone. They are now going to maintain bone. These become these. Imagine a bricklayer who lays bricks all around himself, makes his own personal brick wall, or her brick wall, and they keep moving that brick wall up and up until they completely straddle the brick wall. When that happens, they are making the brick wall anymore because they fix the brick wall. So they start off as a bricklayer, they are an osteoblast. Once they have the brick wall built, then they're just taking care of the brick wall, they're now an osteocyte. This next type is not related to the other two at all. It's actually derived from phagocytes that are specialized in tearing things down. So these, I like to describe it this way, only because it helps me to remember what to do. I describe them as crushing bones, which is not truly correct. But if you think about crushing bone in terms of breaking bone down, then you'd be right. That's their job. They actually release hydrochloric acid and a whole host of enzymes that break down proteins, which is basically what bone is made of. It's made of minerals, which can be dissolved with acid, and it's made of protein, collagen fibers, which can be broken down by proteases. And the osteoclasts make both of these things to break down bone. That's what you need to remember. I say crush because C and build and B. So let's remember which bone cells we want. Osteo means bone. Intramembranous ossification. So there's two different ways that bone forms. The minority way, or the less common way, is this intramembranous ossification. It happens for the flat bones of the skull up here, and the sternum up front here, and even the ribs work that way too. So this very name tells you something about cells, intramembranous. Intramembranous ossification. Intra means inside, in this case. Inside, that means the membrane. However, the membrane is made up of dense, fibrous connective tissue. Connective tissue cells inside form or turn into osteoblasts. So they could take a mask off and say, hey, I'm an osteoblast now. And they basically switch jobs, and they start to lay down spongy bone. Now remember, spongy bone is that bone that leaves like little holes, little cavities. So it's very porous. Very porous. That's my spongy bone. Woo. So we have some osteoblasts that are making spongy bones inside of this membrane. Once that happens, then it starts to make it more solid, and on the outside you get compact bone that fills it in, and that allows for the development of a outer membrane and an inner membrane. Called periosteum. Periosteum around, and osteum refers to osteo refers to bone. A membrane around the bone. So that's intramembranous ossification. Any questions? And the chondral ossification and do means inside here also. Same thing. Chondra refers to cartilage. So interchondral ossification, we actually start off with a cartilage model. This is how we develop as a fetus. We get these cartilage models, which is kind of interesting because the first organisms actually had true skeletons and had a cartilaginous skeleton, and then that got replaced with bone, with bony fishes. And chondrichthyes, cartilaginous fishes, and then the osteichthyes came along with bony fishes. So hyaline cartilage ultimately kind of becomes calcified first because some calcium deposits in there, and makes it a little bit more brittle. There's not really any bone formation here, it's just calcium being dumped in there. On the outside of the cartilaginous model, some osteoblasts will form some compact bone called the collar around the cartilage. So there's a compact disc forming around the cartilage. And that's what they're showing here, showing that we have a long bone. And by the way, endochondral ossification is basically very common in long bones. That's why you're seeing this image. Okay, we're just losing some strength there. The osteoblasts form that collar compact bone. Blood vessels then penetrate the bone model at the diaphysis. So we're using some of the terminology that we're supposed to be learning. That the shaft of the bone here is called the diaphysis, and the ends of the bone are called the epiphysis. So a blood vessel, you can see the blood vessels coming in here. And this bridge was called a primary ossification center. Primary ossification centers in the diaphysis. shaft of the bone. And when the blood vessels penetrate there, they bring in those osteoblasts, they start laying down that bone. We get our primary ossification center. We can see right away it starts off as spongy bone. But eventually, long bones have that internal medullary cavity. And this is where the osteoclasts come in. You're probably thinking, well, if we're going to grow a bone, why in the world are we even talking about osteoclasts? Why do we have these things? Because we do need to break down the bone, not just because a bone gets broken and we have to get rid of the old bone and replace it with new bone, but also because bone is just living tissue and it's constantly remodeling itself to adapt to whatever stresses you're putting on it. So when the bone is forming, it's really important role is to break down the spongy bone on the inside and create this cavity so that the bone stays light enough so you can still move around. And it hollows out that medullary cavity, and then we can put some adipose tissue, and then you get some yellow marrow, and that's a great energy source for us. But principally, to keep things relatively light. Then more blood vessels penetrate the epiphysis, and we get these secondary ossification centers that occur in the epiphysis. So secondary ossification centers in the epiphysis. Obviously, there are going to be two of these. You have two ends of the bone. And the bone that continues to grow and be produced. Now, the epiphysis, we never put that medullary cavity there. We have spongy bone. But the bone is, you can stop the noise for the bone or whatever that is. Well, the bone is actually migrating and migrating, but this epiphyseal growth plate stays in place as long as you're continuing to grow in height. The bone grows longer, that's what makes you taller. And it grows longer because the epiphyseal plate grows, there's more cartilage, and then the bone is also and as you go and slowly become an adult, and this plate gets replaced by a line. The bone catches up, replaces all the cartilage, and it's all nothing but solid bone in there. And so in terms of bone development, that's how the bone, in terms of bone growth and length, that's how the bone grows in length. But in width, it's a little bit different. In width is pretty simple. You think about starting off as a child with a smaller bone, and this will look at the shaft of the bone from the cross center from the top. We'll put a medullary cavity in there. Alright, child bone. And then we want to grow. What we're going to basically do is we're going to start adding bone to the outside. Right? So it's somewhere in between here. We have a bigger bone, but we still have the same size cavity. Now what we want to do is we want to have the osteoclast start breaking that down. So we break that center down, so we get to this stage, we end up with a bigger bone. And we end up with a bigger cavity. So the osteoclast continue to shape this bone so it's the appropriate thickness and weight. So it's simply a matter of osteoblasts adding more bone to the outside, osteoclast dissolving bone on the inside. So osteoblasts add bone to the outside. And osteoclast break down bone on the inside. And so the bone gets bigger and bigger and bigger on width. That's how bones grow. It's a slow process. But a combination of that process can also shape bones, sculpt bones to deal with the everyday stress that you put them to. In order for good bone development and growth to occur, you need vitamin D, you need calcium, because if you don't have vitamin D, then you can't absorb calcium out of your diet. So you can eat all the calcium you want, but if you don't have enough vitamin D, it's going to just pass on through, give you constipation problems. But if you have vitamin D, which you can either get with your milk, because they put vitamin D in milk nowadays, you can take a pill for extra vitamin D, or you can go stand out in the sunshine. It's the one thing that we can photosynthesize, vitamin D. Mind you, you have to deal with UV radiation, the possibility of cancer, too. Always a trade-off. If you don't get enough vitamin D, you don't get enough calcium, and really there's a third factor you need in here, and that is exercise, resistance training for all of your bones. So if you're not moving around big weights in any type of direction you can, even if just body weight, then you don't stress the bones, and the bones are not stimulated to take that calcium that you're eating and absorbing and putting it into your bone. So you need a third factor to stimulate your bones, build up bone. Women in particular are more prone to osteoporosis. That's what this is. This is what normal spongy bones look like here. This is osteoporosis, where the struts of bones are much thinner, weaker, and even broken. And bones break a lot easier and become more brittle. The reason women are tied to having more prone to osteoporosis has to do with menopause and the decrease in the amount of estrogen in the system. Then ultimately, inevitably, osteoporosis is also defined by things like genetics. But lifestyle is a big factor if you really want to improve your chances of not having to deal with later in life. Vitamin D, calcium, and regular exercise. I can't emphasize it enough. We make a hormone called parathyroid hormone. It's a chemical signal in our body made by a gland called the parathyroid gland up here in the neck. Now, when you make it, it increases calcium absorption from the intestines only though it has vitamin D. So basically, parathyroid hormone stimulates the body to take vitamin D and inactive hormone turn it into its active form. And that increases your calcium absorption in your intestines. And that's generally how parathyroid hormone is supposed to work. So what they will often do with osteoporosis, I shouldn't say often, but one of the therapeutic methods for dealing with osteoporosis is to give you synthetic parathyroid hormone along with vitamin D and calcium, so that you will take up calcium in your diet and you will deposit it in your bones, and they will get thicker. But again, without the exercise component, you're fighting an uphill battle. Parathyroid hormone just doesn't stimulate bones to deposit more calcium in general. In fact, if you don't get enough calcium in your diet, you don't get enough vitamin D, either or, the parathyroid hormone, you elevate that. Parathyroid hormone has another effect, a secondary effect, because it's actually a hormone that is released by your system to make sure that the calcium levels in your blood are high enough so that you don't die. Because if your calcium levels are too low in your blood or outside your cells in general, if your cells don't have enough calcium, then they can't do some really important things. Muscle can't contract, neurons don't function, their synapses stop working, and if those things stop working, you don't live. So the parathyroid hormone has another trick up its sleeve. It will stimulate osteoclast cells to break down bone and release calcium into your blood, because it'll rather have you deal with weak bones and still be alive rather than strong bones and be dead, because then you don't have the strong bones at all. So parathyroid hormone is a hormone that's kind of tricky to use. You don't have to have calcium and vitamin D. It actually leads to osteoporosis. In fact, there are instances where people get tumors of the growth hormone and they start producing too much of it, and that causes osteoporosis just because they generally don't get enough calcium and vitamin D to offset all that extra growth hormone. Did I mention exercise? Exercise just acknowledges that bone is living tissue and is constantly remodeling itself to your lifestyle. So if you just sit around and look at the computer all day or your phone and you don't get out and exercise enough, and you got to keep in mind that in terms of speaking in evolution, hunter-gatherers averaged about 6 hours of work a day, not 8 hours, of mostly gathering, chopping, running, hunting, all types of exercise. And then the rest of them, they just kind of loaf around and socialize because that's how we were built. But how many people here are getting 6 hours of exercise a day? I'm not. I exercise a lot. Bone repair, once I break a bone, well, the first thing I'm going to do is going to bleed because we saw which blood vessels were in bone. So that's called a hematoma when you get a big old blood blister inside your bone. The blood is then replaced with basically an infusion of chondrocytes. And these are cells that are going to make cartilage. And they make fibrocartilage because that's the strongest cartilage. We don't need smooth here, we need strength. So we get fibrocartilaginous callus is produced. This is sort of stepwise fashion, and they put numbers on here. Then the osteoblasts come in, and they probably use the milk from osteoclasts, they probably break down cartilage as well as they can break down bone. And they replace that cartilage with a bony callus. So at this point, the bone has become fairly stabilized. Because I got bone in place, but it's still not quite as strong as it used to be. Mostly getting to strength because it tends to be thicker than an broken bone at this point. There's this extra bone that's on the outside. Bone breaks are significant enough that even after you're dead, someone who looks at the bones can tell they've been broken before because the actual scar remains. Even though there's this constant remodeling, and the bone callus does ultimately get replaced with good, strong, compact bone, there's still usually some remnant feature that will show you when that bone has been broken. Maybe again, a thickening. The bone's way of adapting to a break there is to make it stronger so it doesn't happen again. So remodeling will remove that extra spongy bone and reshape the bone so that it's like the rest of the bone. But not completely. There are different types of bone fractures, complete versus incomplete. Okay, so here is a fibula, really thin bone, easy to draw. We get a little point of malleolus down here. If we go all the way through it, we break all the way through it, this is complete. On the other hand, if I don't break one side, I get a little crack on this side, but nothing that go all the way through, that's incomplete. So complete, all the way through. Incomplete. Break. Not. Go through. Do the other side. Well, that's pretty obvious. Let's put it up. So I don't want to take that for granted. Simple versus complex. A simple break, basically the bone is broken, but there's no damage to the skin. The bone doesn't poke out of the skin. It's complex. It usually refers to a break that's either multiple or lots of little breaks in the bone, where you get lots of fragments, or more commonly, they'll usually refrain to use only when there's a break in the skin and the bone is poking out. And those are particularly dangerous because bone is so vascular. If it's exposed to the air, there's a chance to get air bubbles in the blood vessels, and those can actually be life-threatening. Other types of fractures include impacted fractures, where the bone is compressed so much that it breaks just from the force of that compression. And so the risk with impacted fractures is that you end up with bone healing shorter than it was before. And so if it happens on a limb, you might end up with a permanent limb because one leg is shorter than the other leg, or might change the reach in your arms. It tends to be more of a problem with the legs and the suffer more from compression fractures. We learned about wedge fractures in the evolution movie. We talked about vertebrae that compressed to the point where they formed a wedge, and they were broken down so much that they started to narrow on that side. And then a spiral fracture, which is basically just a twisted, ragged break through the bone, so it actually forms at different levels as it twists around the bone. So often the bone itself is twisted, and usually from something like pronation or supination is take it too far and twist the bone so it cracks. These are pretty complex fractures. All right, let's do something different. I wanted to make sure we got through that because that's what the exam is on all the way through that chapter. Can you believe it? We're halfway through the semester. That's 11. Ready? If you'd like to participate digitally, that'd be great. That kind of feedback on some sort of record. You ready? If you're trying to do this analog, you don't want to contribute digitally, then you're going to have to draw a picture of the skull to figure it out. Or you can describe it physically if you want. This is on the zygomatic bone. You got a bunch up here on the frontal bone. I've got one up here on the parietal bone. And I got 4 here where the temporal bone is located. Which tissue is not included in bone structure? Skeletal muscle is correct. Speculae are found in blank. Spongy bone. Trabeculae are found in spongy bone. Most abundant, smoothest, and weakest of the cartilages. Hey, 60 we got it right. Good. Hyaline cartilage. Tiger baby got that one. Got the most points for that. Okay. How many pairs of floating ribs do people have on average? Maybe a question, I'm not really sure what this is showing us. You can give us numbers, just sort of just general where the curve is. How many pairs of floating ribs do people have on average? Pick a number, any number. 2, yeah, exactly. 2 floating ribs. 2 pairs. How many lumbar vertebrae do people typically have? Let's see if we get some answers first. The other numbers after the upper over there. Okay. So just tell me how many people pick that. What's the number? That sounds real fun. Just, so how many lumbar vertebrae do people typically have? 5. There are some people who have more. You know that. Actually, chimpanzees is very quite a bit. Save the best for last. Spinal nerves are found in the intervertebral foramen. You see that was a real problem for you. Okay, hold on. All right, let's talk about Kipchoge here, marathon runner. Ran it 2 hours, 1 minute, 40 seconds. He's absolutely amazing. Muscular system moving the human body. What does the muscular system do for us? What is the function of skeletal muscle? One is support, even though it's not technically a supporting tissue, it's in terms of supporting connective tissue. Nevertheless, it is providing a lot of support for our other softer, more pliable tissues. It helps to stabilize our joints, so it helps to stabilize our bones, support our bones, so we don't fall over. Of course, all the movement that we are capable of is made possible by muscle pulling on bone. If you get cold, you shiver. So our shivering, that's our skeletal muscle contracting. Well, it seems kind of useless because it's not producing any movement. By shivering, the fibers of the muscle actually are rubbing against each other for friction. And they're expending energy, ATP, which means you have to make more energy, and that takes heat. So we maintain your body temperature through the action of skeletal muscle. The flip side of that is really hot, and people typically don't want to do much. They lay about because moving produces heat, causes the muscles to contract, produces friction, produces ATP, creates other chemical energy, creates body temperature, that makes you warm. Skeletal muscle is also important in the movement of fluids. You may think about blood and you think, oh, wait a minute, you must have that wrong. It's cardiac muscle you're thinking of. The heart is what moves the blood through our body. It's certainly the primary pump, but we rely a lot on our skeletal muscle also to help with our circulation. When you are walking around, your leg muscles are contracting. When leg muscles contract, they bulge. So a relaxed muscle, colors I would remember. We have two of these on either side. They all lift pressing upon blood vessels that are in the middle, the blood vessels have valves that point in one direction, upward towards the heart. So when these contract, they press on blood and they push the blood up in one direction. The blood can't go the opposite direction because the valves point against that and they stop the blood from flowing that way. So just by moving around, you're helping your blood move back up to your heart. Also, when you breathe, your diaphragm, which is the skeletal muscle, flattens out. This increases the pressure on the abdominal cavity, decreases the pressure on the thoracic cavity, because whenever you, Wells also said, whenever you decrease the size of the cavity, you cause the pressure to go up. And when you increase the size of the cavity, the pressure goes down. So the pressure goes down here, goes up down here. That pushes blood from high pressure to low pressure up to the heart. So you rely upon your skeletal muscle to help good circulation. I've given you another reason to exercise. Another fluid that's less appreciated, and unfortunately, I don't normally have time to talk about it in this class. I think that maybe this semester will be different. There's a fluid called lymph. It turns out that our circulatory system is not perfect, so we often lose fluid from our blood vessels and it ends up in your body's tissues. And there's a secondary system of vessels that are called lymphatic vessels, and they collect that lymph and they return it to your blood, to your circulatory system. But lymph vessels don't have a heart. They don't have a lymph vessel heart. So the lymph system relies entirely upon skeletal muscle and you moving around to collect that fluid and return it back to your circulatory system so that you can filter it through your kidneys and get rid of excess fluid. One of the things that can lead to increased edema, increased buildup of bodily fluids in your body, is simply just not exercising enough, sitting around. The fluids don't get returned to the blood like they're supposed to, they stay in your tissues. So it's a really critical part of the skeletal muscle system is to manage your volume of all your fluids in your body by moving them around. And then protection. Your abdominal muscles protect your abdominal organs. There's no bone down here. All you've got is muscle for protection. So if you are neglecting your abdominal muscles, you're neglecting the protection for your abdominal organs, and they're kind of important. So those are some functions of the abdominal muscle. Any questions? There's some basic structure for a muscle. So they're showing us the connection of this one muscle to some bone. And they pull the muscle up and they're showing they remove some connective tissue. And we see that muscle is organized into groupings of muscle cells called fascicles. So when they say muscle fiber here, a muscle fiber equals or is a muscle cell. So bundles of fibers are called fascicles. These in turn are covered by dense fibrous connective tissue. So they've got connective tissue, and then the whole muscle has this fascia. Which is the connective tissue covered from the muscle. All of that connective tissue, the muscle itself, the actual muscle tissue itself, does not make a connection to the bone. That connection is accomplished by connective tissue, what called connective tissue. So it's for the glue of the body. So all that connective tissue comes together and forms what's called a tendon. And the tendon is what attaches to the bone. And sometimes the tendons are very broad and connect to the bone very broadly. But they tend to focus on the more convergent fiber muscles where the tendons are relatively narrow. There are some tendons that are very broad in their connection to the bone. So the tendon is also connective tissue. Muscle so we already talked about bursae. Bursae are important in terms of reducing friction. So we might put a bursae between the tendon here and this bone. Wherever they are, they're going to reduce friction. In this particular example, they reduce friction between tendon and bone. But it could be tendon and skin, any number of things. When you look at a muscle fiber up close, microscopically, you will see inside of it has even smaller, what look like fibers. But since we already used the word fiber, we can't use fiber again, so according to what we call these are fibrils. So fibril is a really small fiber. So we say myofibril, myo means muscle, fibril means basically the small fiber. So inside of a muscle cell, there are lots and lots of these myofibrils. When you go to the gym to work out to increase the size of your muscles, you're usually not increasing the number of muscle cells. What you're doing is you're increasing the number of myofibrils, or the thickness of myofibrils, and then eventually it gets so thick that they split and you get two myofibrils in one. Let's go ahead and take a 10-minute break. Organ. This is the muscle attachment point. As it moves, during contraction. Insertion. Muscle attachment point. That moves during contraction. So biceps brachii muscle, this is what this image is showing you. Flexion of the forearm. The part that moves, maybe I should start with the part that doesn't move, is up here is the scapula, attached to the coracoid process and the supraglenoid tubercle. They don't move when you're flexing your arm. Scapula stays stable. So that's the origin. Down here, the muscle inserts on the radius, also called the radial tuberosity, because the radial tuberosity moves when you contract that muscle. So that's its insertion. For flexion of the arm, that is, that muscle is the prime mover. That's what forms all the force for flexion of the arm. So, agonists provide most of the force for a given movement. A synergist is best to think of it as a helper muscle. It adds to the force of contraction. That's a simple way of looking at it. There's actually different types of synergists. So one of the things that did not include in this picture is synergist. But there's a muscle that actually crosses over the elbow joint here. It starts up here at the lateral epicondyle of the humerus and goes all the way down the radius to the end of the radius. It's called the brachioradialis. Because it crosses over this elbow joint, it helps with contraction of that, helps with flexion of the antebrachium. But it's not at a very good angle to do it. It's a pretty big muscle. It's the muscle that forms the top of your forearm right here. But it doesn't cross the wrist joint. And it doesn't really get far enough on the elbow to really do a lot with this motion. It helps a little bit. So it's considered a synergist. For every movement, you always have a muscle that's going to work opposite that movement or produce the opposite movement. In this case, the tricep brachii is that muscle. So the antagonist works against the prime mover, works against the agonist. And produces opposite movement. In other words, the tricep brachii produces extension at the elbow, and so by default becomes the antagonist for contraction and for flexion at the elbow. So when you're talking about agonist, synergist, and antagonist, but particularly when you're talking about agonist and antagonist, you have to consider the motion you're talking about. If you're talking about extension at the elbow, if that's the action you're talking about, the prime mover for that action is the tricep brachii. It causes the extension at the elbow. And the antagonist to that motion becomes the biceps brachii. So the roles get reversed when we talk about the opposite movements. A synergist for that would be a little muscle called the anconeus that crosses over the elbow joint back here and helps with the extension at the elbow. I'm not going to test you on specific synergists here. I just want you to understand the definitions. You can also do something similar with origins and insertions. You can flip them depending on the action you're talking about. The biceps brachii is not a good example of this because it either causes flexion at the elbow or flexion at the shoulders. It doesn't really flip its origin and insertion. In either case, it kind of stabilizes the scapula, and the insertion really remains the same. But a good muscle for this would be the sternocleidomastoid, which is the muscle on the side of your neck here. Because it actually attaches to the mastoid process on the skull and to the sternum and clavicle up front here, it can do one of two things. It can flex your head, both of them together. And when it does that, its insertion into the mastoid process is moving your head, right? And its origin is the clavicle and the sternum. That's what its name means, sternocleidomastoid. Sternum, cleido, clavicle, mastoid process of the skull here. But it also is a muscle that helps you with breathing. So take a deep breath. If you take a breath that's deep enough, your sternocleidomastoid muscles will contract to lift the sternum. And when it lifts the sternum, it lifts the rib cage. And it lifts the rib cage, you breathe in deeper. You get a bigger breath in. You get more oxygen in. Under those circumstances, the insertion becomes the sternum and the clavicle, and the origin becomes the mastoid process. And again, I won't really touch you on those two muscles and other organs and insertions, but I just want you to know the definitions. But give you an appreciation for how those are used and how they can be flipped. Just a note, there are a lot of muscles that don't move limbs. We tend to focus on that. Think about your facial muscles and all the facial expressions you're capable of, whether you're smiling or looking silly. We are one of the few animals that can do that. We have facial muscles that we have control over. There's not a lot of animals that can do that. They're much more limited. Dogs can snarl at you, but they can lift their eyebrows a little bit, but they don't have the same range of expression. And it's probably mainly because we don't have a lot of fur over our face anymore. We can actually see what's going on with the face. We have those ways to communicate more verbally. Breathing, I just mentioned breathing. So there's some muscles that are involved in moving the axial skeleton around. And that's what we're talking about with breathing. We're talking about axial muscles that move the axial skeleton, lift the rib cage, move the vertebral column. So we can do this, hands. Move the head, which of course is one of them, move it around. And of course the mandible for chewing and speaking. We need to move that too. So we have axial muscles that are doing that. All of those muscles, everything there is axial. It's not moving a limb. That's the very definition of the appendicular muscular system. It's muscles that move the limbs. Any of those is any part of axial structure or is involved in facial expressions or axial muscles. Questions? Okay. This is the list. There are over 600 muscles in the human body. So this is by far the short list of muscles that I would like you to have the actions for memorized, not for next week, right? Because this chapter is not going to be on exam 2. This chapter is going to be on exam 3. Everything on muscles is on the next exam. But I have to start covering it now because this is when I have the time to cover it. All right? Exam 2 is only going up to the skeletal system. So by the time we get to exam 3, you need to have these memorized. Or have it on your exam sheet. So muscle actions, the auricularis oculi is a muscle involved in winking. The masseter muscle is a muscle involved in chewing. It's a muscle inside the cheek here. The orbicularis means circular. So these are muscles that have form circles around the structure. So around the oculi, the auricularis oculi, for winking. Winking is a forced closure of the eye. Usually we close our eyes by just relaxing a muscle called the levator papillary superioris muscle that is responsible for elevating the eyelid. But you can forcibly close the auricularis oculi. And the auricularis oris allows you to pucker up. So that's why I call it the kissing muscle. Masseter is for mastication. It's not the only chewing muscle. It's actually not even the biggest chewing muscle, but it's a powerful one. So it's worth mentioning. And it's the one that your book has decided to show. So in case you're wondering how I came up with the list, I just looked over here and said what muscles did they list over here. And that's what's over here. This actually makes it look short. The pectoralis major, So you will see that I do change things here and there because we just finished learning a bunch of actions, motions, and I want you to use those. So the pectoralis major is not bringing the arm forward across the chest. That's flexion of the arm. Not the forearm, but the actual whole arm. The deltoid muscle, I'm not sure, it brings the arm away from the, that's literally the definition of abduction. So you can say abduction of the arm. Biceps brachii, flexion at the elbow. Bends forearm at elbow. Stratus anterior muscle. So let's talk about some of these other names here. Pectoralis major, the pectoral region is your chest region right here. You actually have a pectoralis minor muscle underneath it. It has nothing to do with moving the arm, but it's in the same region, so it has the same name, except for it's minor, not major. The deltoid is named for its shape. It's a triangular shaped muscle, and the Greek letter for delta has that same shape. Let's say the Greek letter for D is kind of like that. The biceps brachii, biceps means two heads. Bicephalon. Brachii is in the arm. There's a reason for putting brachii in here because there is a biceps femoris. Stratus anterior gets its name from the fact that if you look at the edge of the muscle, it looks like it's serrated, like it's got a serrated knife. You come into it. That's basically because the fascicles of this muscle interleave with the fascicles of the external oblique muscle here. The stratus anterior moves the scapula. We didn't learn about protraction, so I did not put that in there, but basically it moves the scapula forward. You reach for something, that is an important muscle for that motion. The external oblique muscle or your abdominal muscles are ones of your four abdominal muscles. These are on the outside, is why they're called external. They're oblique, it means the fibers are going at an angle to the midline of the body. And you can see here this involving compression of the abdomen. For some of these, I've shortened up the action, so it makes it easier for you to memorize. Create some flesh parts. So when I talk about memorizing anything, I'll just put this on my cheat sheet. Keep in mind that anything you can memorize is something you will have to put on your paper. So you want to be strategic about that. You find things that are hard for you to memorize and put those on your paper. And the other thing, you want to practice memorization because it's just frankly a good skill to have in life. The quadriceps femoris is a big muscle. Nowadays we call it the quadriceps group, and there's actually four muscles in there that are identified separately. But since that's what they're using, I'll stick to that. It's a big muscle. Quad means four. Basically has four heads, what they're saying. They only pointing to three of them because the fourth one is underneath that muscle right there, the rectus femoris. This is a really important muscle for kicking, for moving your leg outwards. It's actually extension of the leg, is probably what I should have put there. But like kicking is a good way of thinking about it. And because the rectus femoris here crosses over the hip joint at a structure called the anterior iliac spine, you can raise your knee up because of it, so it helps with flexion at the hip. The tibialis anterior is named for the fact that, quadriceps, four heads, femoris because we're in the femoral region where the femur is. Tibialis anterior, the tibia is right there. Anterior means in front of, so the tibialis anterior is in front of the tibia. And it's in a position basically, if you go ahead and take a moment, I want you to try to touch your shin with your big toe. Oh wait. That's right. I didn't think that was possible until my grandson was born. Babies can do it. Like their foot bends all the way up, it's like crazy. But anyway, that's the motion. You point your toes up towards the sky. That's what that muscle does for you. So you can imagine we don't use that a whole lot. So it's a pretty small muscle. And in a minute we'll see we have these big calf muscles on the backside. So if you do decide to take up running, one of the problems that you encounter is this imbalance between the front muscle and the back muscle if you're not used to running. And these big muscles pull so hard they end up tearing that front muscle a little bit. And people call it shin splints. You usually get used to it, or unless you're wearing the wrong shoes or have a bad stride. So it's something you can usually work through that. I remember I got it when I first started taking the frame. I was like, oh, I'll never do this again. But I kept on moving that way. Extensor digitorum longus is actually right next to the tibialis anterior. So extensor tells us what it does. It extends the toes, the digits. So you curl your toes, and then you extend your toes. So it's the opposite to curling your toes. It also raises your toes and also acts as a dorsiflexor, but we're going to just leave the extended toes. That's easy to remember. It's a muscle of the leg. The rectus abdominis, back up here, the abdominal muscles. The rectus abdominis is what's responsible for that six-pack. If you can get your body fat levels down low enough and show this muscle off, we can sort of definition out of it. It's responsible for flexion of the trunk. The flexor carpi group, I mentioned here, there's a whole bunch of muscles in here. Carpi means wrist. We talk about the carpal bones. Flexes the carpal bones, flexes the wrist. So flexes the wrist. The adductor longus muscles adduct. So if you bring your leg out like this, you want to bring it back in, that requires the adductor muscle. There's a whole machine at the gym where you basically practice bringing the thighs together, puts this weight up, and works out the adductor muscles. There's a whole bunch of them, adductor longus, adductor magnus, adductor brevis, and the supercilious muscle. They all help with that. Even the sartorius helps with that. We have a lot of things for the sartorius, but I've cut this down pretty easily for you. So the adductor longus moves the thigh towards the midline, in other words, it adducts. And the sartorius laterally rotates the thigh. So we're going to focus mostly on its lateral rotation. You can see just the way it's kind of a funny muscle. It's a little strap here that crosses over the front of the thigh and then crosses over the knee joint and connects over here. So depending on where it contracts, it does a bunch of different things. It's mostly a synergist muscle, which you can raises, laterally rotates the thigh, like crossing the leg, kicking across, and soccer. But it doesn't provide a lot of force to any of those. It's pretty weak muscle. Now we flip the body over and we look at some of the muscles on the back side. So the trapezius muscle is way up here. It's a big muscle, extends all the way up to your neck. People are rubbing your neck out, giving you a massage. That's what they're rubbing on, the trapezius muscle. It's a big muscle, so it does a lot of things. I've only included a couple of them. One is it extends the head, and the other one, the fibers can raise the scapula. So if you raise your hand, the scapula comes up a little bit too, and the trapezius helps with that. People will do rubbing exercises to exercise this muscle. But it brings the scapula down. Also, when it brings it out, it adducts it too. The latissimus dorsi. So trapezius is named after the fact that it looks like the shape of a trapezoid. The latissimus dorsi, latissimus means wide, and dorsi means back, the dorsal region. And it is involved in adduction of the arm, so bringing your arm down. Didn't talk about the pectoralis major helping with it, but it also, the front side is muscle responsible for that. The back side is latissimus dorsi. So if you're doing pull-ups, this is one of the muscles you're working out. It's the one that most people focus on, but it's really important for the pectoralis major too. The tricep brachii muscle back here, extension of the arm, we work out the tricep brachii. The extensor carpi group back here again, there's a bunch of extensor carpi muscles here. Sadly, this image is actually labeling one of the flexor muscles that way. I don't think someone was paying much attention when they did this. The extensor carpi is basically responsible for extending the wrist. The extensor digitorum muscle is going to extend your fingers. Notice that extensor digitorum versus extensor digitorum longus. Longus is for the leg or your toes, and this extensor digitorum is only for your fingers. Differentiate between those two muscles. It's a common mistake and lecturing him to get those two up. Gluteus maximus is responsible for extending the thighs or extending your leg backwards, the kicking back in order to pull yourself forward. We rely a lot on this muscle so we don't fall over. The biceps femoris. It's interesting that the previous slide they grouped all of the front muscles into the quadriceps group. But here they have a chance to group all these into the very well-known hamstring group, because that's what these typically are called. But they said they picked out one muscle from that group. I don't know why. But anyway, it's a good opportunity for to compare it to the biceps brachii. The biceps femoris is in the femoral region, and the brachii is in the arm region. Now, where the biceps brachii is involved in flexion, the biceps femoris is involved also in extension of the thigh, but it also flexes the leg. So what that basically means is if basically again kicking your leg out, extending your thigh, that's a hamstring activity. But the flexion of the leg, kicking that heel up, is also part of the biceps femoris. And that's because this muscle on the lateral side of the hamstring actually crosses over the knee joint. It has two heads, that's why it's called biceps, and bicep will have two heads. One of those heads, the short head, attaches to the femur and only crosses the knee joint. But the long head goes all the way underneath the gluteus here to attach to the ischium on the pelvis. And it crosses the hip joint, and that's what allows it to extend the thigh. Gastrocnemius, gastro means belly, and somehow nemius refers to the fact that it's two bellies. I don't know the connection there. But this is important for plantar flexion of the foot, which basically means standing on your two foot. It's not the only muscle that's involved in that, but it's a very large muscle, and it's the one that's mostly involved in active pushing around. I do have one structure here, because it's mentioned in this image, that's not a muscle at all. So it is a tendon, and that's Achilles tendon. And that's what connects the gastrocnemius, along with other big calf muscles, to the calcaneal bone here, which allows you to stand on your toes and push off with your foot during running to do this kind of work. It's a big, thick tendon that stores energy very efficiently. Any questions? So I've already alluded to some of this, but just to give us some redundancy and repeat some of these terms, muscles are named for a lot of different things. They're named for their size. Usually when they use size for a name is because there are different muscles that are in the same area with the same name otherwise. In other words, if you don't add something there to differentiate them, they sound the same. So you have a rhomboid major, you have a rhomboid minor. One is bigger than the other one. So the main based on the size of both rhomboid muscles, but they have different sizes, and that's how we differentiate them. The pectoralis major, the pectoralis minor. The gluteus maximus, there's also a gluteus minimus. There's also a gluteus medius, or in the middle. Other times they're named for size just for the heck of it. So vastus, the vastus lateralis of the quadriceps group, the vastus medialis, the vastus intermedius, those are the ones that have vastus that I remember. They just mean big. Longus and brevis are often used together because you'll have the adductor longus, you have the adductor brevis. Same adductor, they do both do adduction, but one's longer than the other one. Brevis means brief or short. That's okay. I thought everyone knew that, but I found out recently that was not the case. The thing about this is being brief, which basically is another way of saying short. Otherwise, muscles are named based on their shape. Deltoids, this is the Greek letter deltoid, or delta. the deltoid muscle looks sort of like this. So it's sort of an inverted delta. And then trapezius is for a trapezoid. I'm not sure if latissimus really belongs in shape. It sounds more like size to me. Because latissimus means wide. But teres, we don't talk about either the teres major or the teres minor. It means round. So if I can name that. We did see some location names for the external oblique. On the outside. Usually, again, that's something that's saved for when you have muscles that share the same name, but they're located in different orientations to each other. The pectoralis, which is in the chest region, so pectoralis or pectoral. Frontalis means right here in front, right in front of the frontal bone. And then the brachii means arm. And then femoris refers to the femur. Ultimate thigh here, so maybe common term connection. The direction of the fibers is important for some muscles. All the abdominal muscles kind of fit this bill. You have the rectus abdominis, you have the transverse abdominis, you have the external oblique and the internal oblique. So all the different directions covered here. Everything about rectus. Fibers are going straight. You think about transverse. Fibers are going straight across. Now you think about oblique. Fibers are going at an angle to. So by having transverse, rectus, and oblique fibers are around the abdomen, you have muscle fibers going in all different directions, protecting all of your abdominal organs. Orbicularis means circular. So then we can draw circles for the orbicularis muscle. So I mentioned the sternocleidomastoid earlier. Middle name for this is mastoideus. Sterno refers to the sternum. Lido is clavicle. Mastoid refers to the mastoid process of temporal bone. Brachioradialis is actually, that's the, well, I mean, it's okay. But basically, we never talk about brachio, I mean arm. Radialis refers to the radius. Number of attachments or heads, biceps is 2. Technically, that's it. Let's do it that way. 3. And then quadriceps. What doesn't get used all that much? And then action, does it flex? Does it abduct? Does it bring the body part back towards the midline, and then levator basically means the elevate. So you have a muscle called the levator scapulae, which is responsible for lifting the scapula. And also the trapezius in that reaction. Questions? Okay, so here we have the detailed diagram of a muscle cell. Remember that a muscle cell is the same as a muscle fiber. And we're going to zoom in to look specifically at those myofibrils. So you can see here at the top, they're showing us that earlier, well, it's not exactly the same image, but sort of similar to it, where they're showing us the muscle, the bone, the tendon, and they pulled out one of the fascicles, they pulled out one of the muscle fibers, and now they're pulling out one of the myofibrils, and that's what we're seeing as the muscle fiber, muscle cell. There's one of the nuclei, you can see that it's multinucleated, and we pulled out one of the myofibrils. Remember, myofibril means muscle, little fiber. It's a muscle cell, it's a cell, so a cell must have a membrane. So it's really just a cell membrane. It has a special sarcoplasm. Is the muscle cell's cytoplasm. Remember that myo means muscle. Does myoglobin sound familiar at all to you? Anybody? Have you heard of hemoglobin? Well, hemoglobin is a protein in your blood that carries oxygen. Myoglobin is a protein in muscle that carries oxygen. In fact, it has a higher affinity for oxygen than hemoglobin does. So what happens is the blood brings the oxygen in with bound to hemoglobin, then it gets really close to myoglobin, and the myoglobin steals it away. It has a greater affinity for it. Just because muscle cells need a lot of oxygen in order to generate ATP. A lot of times, not all the time. But typically we tend to find more myoglobin in muscle cells that are built for endurance. We tend to find less of it in muscle cells that are built for quick action, because they tend to use anaerobic respiration instead. They don't use oxygen. You saw what I did there. I'm trying to magnify this image here so we can see those green lines a little bit better. Unfortunately, it's up being a little blurry because the end up being blocked by the picture. Basically because the pixelation is a little bit low for that side. But the idea is that these these T-tubules are really extensions of the sarcoplasm. So we're looking at a muscle cell. down the myofibril, and then it comes back up again. That forms like this loop, and then it goes back to the circle. Here's my T-tubule. It stands for transverse, by the way. And then passing through this, of course, is ultimately the myofibril. So it's not a hole, it's like an extension of the circle on the down. And this allows for any signals that might be transmitted on the surface to get down deep and get to where they can actually get to this myofibril. And that's what that transverse tubule is all about. Communication. Sarcoplasmic reticulum. This is the muscle cells, endoplasmic reticulum. Does a slightly different job than what we learned about endoplasmic reticulum before, but effectively that's where it gets its name from. And we find it on the surface of the myofibril in a way that allows it to get real close to the transverse tubule. And it's pretty expensive. Kind of setting the stage here. We're going to talk about how muscle contracts, and in order to do that, I have to talk about the players on the stage. I have to tell you about what the different participants of this action are going to do. Not all of them have a role, but many of them do. That one definitely does. We always use myofibrils, we use fibers, and yet, if we get small enough here, we look closely at the myofibril, we notice this is made up of lots of little filaments. And so we call those myofilaments. Again, just being a filament, muscle. When we look closely enough, we can see that even that they're not all the same, they're made of different stuff. When we look at these myofibrils, we also notice that they are organized. And that there are these discrete units along the length of it. So I pull this out again. So there's a lot of stuff going on here, but then this picks up over here like so. It has more extension, and then it has more of these thicker filaments in here. And then farther down, there's another one of these. And this pattern just keeps repeating itself. And so they start defining these different areas, and they said that this is out here from one zigzag line to another zigzag line, and we're going to call that a sarcomer. And that's where all these sarcos are coming from. Sarco, sarco, sarco. all these sarcos are coming from that sarcomere, because the sarcomere has all of the functional components necessary for muscle contraction to occur. So everything we're going to talk about here in a moment talks about how muscle contracts is related to what's going on with the sarcomere. So we're showing that here the sarcomere relaxed, where it's all stretched out, versus the sarcomere contracted. This is where muscle contraction occurs. The sarcomeres contract, the muscle fiber contracts. That leads to muscle contraction if enough of them contract. It's kind of weird because the muscle does not contract proportionally to how the sarcomeres contract. All sarcomeres do is add tension to the muscle. When there's enough tension in the muscle, then the muscle gets shorter, contracts, and we get muscle contraction. I'm going to let you guys go out a little bit earlier than today. You have a lab exam you probably want to think about a little bit and find where I want to be.